So we're going to stay with this innovative farming solutions theme, and we're going to take it from the field, which we just heard, and more into the research realm. So as we do that, I'd like to call Dr. Daryl Martin forward to the front of the stage. He is going to be both the moderator and presenter, the final presenter for this next panel. Many of you probably know Dr. Martin, but if not, he is a professor of biological systems engineering at UNL and also an extension specialist in irrigation and water resources engineering. So I'll have Daryl, wherever you're comfortable, Daryl, I'll have you.
Okay, well, thanks very much. I guess our point on this session is to talk to you about the research that we've been doing. We're going to go over a wide range of things here. So we're kind of going to go with a batting order, kind of starting with the agronomy folks. So ask Charlie to maybe start and summarize some of his work. And then I believe Andrea's going to do the next one. And then Amy will talk, I think, about some animal issues. And then I'll try to summarize a little bit of stuff that we've done in irrigation and nitrogen management. I'll just ask you to introduce yourself a little bit, and we can go from there.
All right, so Charlie Wortmann. Actually, I grew up about 55 miles northeast of here. So I have siblings, in-laws, nephews, nieces, cousins who are farming the northern tier of counties from Boyd, Knox, Cedar, Dixon, as well as some north and south of there. On the other hand, maybe I'm not a very good humanist because I don't understand why some people do the things they do, as Wade was pointing out the excessive amounts of nitrogen and water that some people put on. I was asked to speak about nitrification inhibitors, controlled release products, etc. But I am going to go into some other things because, frankly, there's not that much new on them. So we have a diagram here, and maybe some of you cannot see it from the back, but we're starting with urea, the urea compound on the left, and then what happens to it as we move along. And one way to control the release of nitrogen from the fertilizers is to have a slow release or controlled release products such as methylene urea or polycoated urea. But there's been a lot of interest in, inhibitors of nitrification, which are listed here, and I've written them in larger font size there. Some of these have been around since the 60s. And a lot of research has been done. And the research results I'm going to show you mostly are from decades ago, because not that much has changed. With the slow release compounds, such as methylene urea, let's see, there's something not showing. There it is. Here on the left we have, this just isn't working well. There we go. That would be better, yes. Is this on? All right. Sorry about these complications. So on the left, we have what might be nitrogen availability from urea on these curves. And then with methylated urea, the release rate changes as the size of the compound increases. So it can be designed for different releases. And here we have one that might be releasing a bit early relative to the uptake of the corn. This one might give us a better match, and here it's generally too late. So the idea is that the products like this are there to improve the synchrony of supply with demand. And then we have our poly-coated products, which are actually large granules of urea coated with polymers to allow a gradual release. And their effectiveness has been confirmed in Nebraska, especially with some sandy soils. They are for conditions of high nitrogen loss risk with early season application. There's no point in putting them in during the season because you can get by then with less expensive fertilizers. The polymer coated needs to be properly designed because it can result in too slow or too quick release of the nitrogen fertilizer. And they can be carried by runoff. They're less dense than water, so if it's surface applied, which it generally is, there is that potential that it could be carried by runoff. And there has been some evidence of increased ammonia volatilization with these products. These products, as well as inhibitors, they're very well addressed in this extension publication, which Dave Franzen from the North Dakota State University is the lead author on, but it was written for the North Central region. So the information is widely applicable. Here are some research results. This is a case of fall application. You see the date of application was October 14th. Then we have days since application. So they made their first observation on the ammonium concentration after application about 20 days after application, or maybe 15 days. We see that the light gray line, which is what the inhibitor applied, and in this case the inhibitor was nitropirin, had much more to nitrogen in ammonium form as compared to where no nitropyrin had been applied. But we see then after that the lines are pretty much parallel, meaning that already 2 weeks later, 20 days later, the effectiveness of the inhibitor was gone. More important is that if our main leaching occurs between May 1st and June 10th, which I think is right, it's when we have our greatest potential. We see that starting at May 1st, we don't have much in ammonium form anymore. So this is a case where they looked at fall application of the inhibitor. It's not effective for stopping leaching in May and June. This is a case of spring application, applied April 5th, and again we have days after application on the x-axis, and a change in ammonium concentration in the soil where they applied it following that. And so we see here, even after 20 days, the first sampling of the soil was about 20 days after application, there was no effect. And apparently it was because the temperature was low enough that nitrification was not taking place. We do see we have some protection of the inhibitor, again, the light gray line, so that by the time we expect our main leaching events to start, quite a bit of it is still in ammonium form. So this situation suggests that with this application, it should be quite effective in reducing leaching of nitrate nitrogen. These are some similar results. I should point out that this research was already done in 1970s, mid-70s, published in 1978. Here's some from 1984 and 1985. On the top, the two figures are for fall application, and we have some for spring application. And again, it shows that with fall application, we're not likely to have protection from the nitrification inhibitor in May and early June. Whereas with spring application, there is a significant amount of protection, especially here, although the application wasn't until April 20th. But here as well. So with spring application, there is potential to do yourself some good. With fall application, there is very little potential to help yourself in the reduction of nitrate leaching. A study from South Central Ag Lab in Nebraska. It's a silt loam soil. It's continuous irrigated corn, and it's been underway since 1986. They looked at different N rates, different tillage practices, N application times, and use of an inhibitor, nitrification inhibitor versus no inhibitor. Some results with the pre-plant nitrogen, there was a yield increase in 6 out of 20 years and yield decrease in 1 year, with an average yield increase of only 2.12 bushel. So not much gain to attempt to pay for the inhibitor. This is with pre-plant application in the spring, anhydrous treated with N-Serve. With side dress application, there was a yield increase in 1 year, a decrease in another year. The average change in yield was about 0. These are the results of deep sampling to 9 meters, about 30-foot depth. And the sampling was done for the 150 kilo or 134 pound nitrogen rate and for a 268 pound nitrogen rate. The red is with inhibitor, the blue is without inhibitor. So we're seeing with the lower rate, really no effect on nitrate concentration across the soil depth. With the higher rate, there's some variation, but sometimes it's lower with the inhibitor, sometimes it's higher. This shows the cumulative nitrate in kilos per hectare in the 9 meters of soil. So we see a very big nitrogen rate effect, but the inhibitors over those 20 years did essentially no good on this silt loam soil, telling us if the inhibitors are likely to be useful, it's going to be with higher, coarser textured soils, such as sandy loams, loamy sands. So some summary on the inhibitors. We're not likely to see much yield benefit or effect on leaching for a silt loam or a silty clay loam soil. The inhibitor is most likely to be effective with spring application, very little potential for benefit with fall application or with in-season application. The polycoated urea, in other studies, a lot of results I haven't presented, was more effective than the inhibitors. It is an alternative to in-season application for soils with high leaching potential. Again, sandy loams are coarser, but it does have a high cost. The duration of inhibitory effects depends on soil temperatures, and maybe only 2 weeks with higher temperatures, say 65 degrees and above, but longer with low soil temperatures. Nitrification inhibitors can have a small role in nitrate-N reduction when use is timely and well targeted to high-risk situations. So again, coarse soil, corn after corn, and with spring application. So going on to something else, practices that might complement inhibitors or be alternative to inhibitors. This image is from the 2018 crop layer. And we see the colors dominated by the gold. The gold is where we have corn production. Green, the dark green is soybean production. The light green is hay or pasture. There are some pink areas that are alfalfa, some gray areas such as over here, which are towns. This should be the town of Wayne. So this image is for the counties north of here. So what we see is a lot of the yellow gold color, right? Implying there's a lot of corn after corn. Economically, that may be best, especially if you're supplying a feeding operation or an ethanol plant. But for control of nitrate loss to groundwater, it's not good at all. And we addressed this in an article in Crop Watch this spring. If you don't know Crop Watch, it's a regular newsletter that comes out at cropwatch.unl.edu. Our nitrogen use efficiency with the corn-soybean rotation is really very high on average, and close to as high as we can push it. But with corn after corn, it's pretty poor. Maybe only 65% recovery of the fertilizer nitrogen equivalent. And so that's a very leaky part of our system, is planting corn after corn. One of the speakers spoke about alfalfa, and yes, the demand is limited. But if you want to control nitrate leaching, especially for the wellhead protection areas of your communities, this is really something to be looked at. First of all, if you have, say, alfalfa 5 years in a 10-year rotation, say 5 years of alfalfa followed by corn-soybean rotation for 5 years, you reduce your nitrogen, fertilizer nitrogen requirements by about 60%. And it's much more reduction compared to corn after corn, of course. It's deep rooting. It'll remove the nitrate down to 10 feet, and other evidence shows to 12 feet. That you also are irrigating it likely, which means pumping up a lot of nitrate. All of that nitrate gets removed from the field. And profit-wise, with current markets, it can be kind of competitive with the corn-soybean rotation. So we can be criticized on the economic analysis that we use. Maybe our pumping costs were not high enough, or we didn't put on enough irrigation water, or another was that, well, your alfalfa yields are too low. So we developed this calculator. It's available through this article, and you can put in your own values and look at the profit potential with it. And again, as Rick, if I remember your name right, the market is limited, but if you can attract a dairy or two to the area, that could greatly increase that market. And again, you're most concerned about the wellhead protection areas. So it's not so much acreage that we're talking about. Amy will say more on manure use efficiency, but I just want to include something very briefly. The manure nitrogen we apply is equivalent to about the fertilizer nitrogen applied to about 1 million acres of corn in Nebraska. We don't give good credit to that. There's evidence that it's not adequately credited. And there's some reason for it, because it's difficult to predict how much nitrogen you're going to get from that manure in a given year. But we did 23 site years of research, and that we completed in 2018. Among other things, looking at the potential of adapting the sensor technology for reading the crop canopy sensor for manure fields to see how much nitrogen was needed yet. So you make up the difference with in-season nitrogen fertilization. And there's another article in Crop Watch from this spring that addressed that. We need to be looking at improvements that have additional benefits with high cost effectiveness. Very often reduction in nitrate leaching can be associated with reduction in nitrous oxide emission. Nitrous oxide is probably the most important greenhouse gas we need to be concerned about with crop production, and it has big implications. So I did a quick economic analysis with $3.50 corn, 40-cent nitrogen, and I assumed that N loss to 30-foot of vadose zone, which was based on a slide I presented earlier, is equal to 0.2 pounds of fertilizer N per pound of fertilizer N. That is, the amount leached is 0.2 pounds per pound of fertilizer N applied, in excess of 135 pounds per acre. If we were to reduce our nitrogen rate by 25 pounds per acre, from 195 pounds to 70 pounds, that would reduce our net returns to fertilizer nitrogen use by less than $3 per acre, because we're at that part of the slope where gain in profit has greatly diminished as you put on more fertilizer. We would reduce our nitrate-N leached in the 30-foot vadose by 4.8 pounds per acre, which comes to, sorry, there's a problem with the calculation. And we would probably reduce our greenhouse gas emission, expressed as carbon dioxide equivalent, by about 145 pounds per acre. So we can achieve these two benefits, with that simple reduction in the nitrogen rate of 25 pounds per acre at very low cost. All right. So, and that's, okay, this is just a summary. I want to say something. A few years ago, we were talking about climate weirdness, the onset of climate weirdness with climate change. That has proven true, and it's likely we're going to have more extreme weather events in the future. It's going to make all of this work much more complicated. So if we're going to do something about it, we do have to be very serious about it. It's got to go far beyond rhetoric.